embedded AI on drones is different than embedded AI on humanoids or serial robotic arms. But in essence, they still have to observe, they still have to come up with some mechanism to learn actions and apply those actions, as well as reason as the environment changes. And the physical AI environment will constantly change. The reason I mentioned game theory, and it's an amazing mechanism to optimize your AI models, because they become in tune to the fact that you may be facing intelligent opponent. You may be facing intelligent collaborator, and the result, you need to also adapt your actions based on those. You cannot control the environment in which you're going to push the drones. Look at the war in Ukraine. I don't think they can emulate every possible scenarios which they're going to face in the real world. That's my point when you perceive what is the mechanism that we need to have in embedded AI that learns and adapts quickly with limited data.
Welcome to ODSC's AI X Podcast, your gateway to the latest in everything AI. Whether you're a seasoned AI expert or exploring how to bring AI into your work or career, we bring you insights from the best minds in the field. We host researchers, practitioners, and industry leaders shaping the future of AI and how it's being applied across research, product, and industry. This episode is sponsored by ODSC AI East, the premier AI Builders Conference, coming up this April 28th to 30th, 2026 in Boston and virtually. Learn more at odsc.ai/east and use the code podcast for an exclusive 10% discount. We're also bringing back the Agentic AI Summit, a virtual 3-week conference this January 21st to February 5th. Learn more at summit.ai. Sheamus McGovern, the founder of ODSC AI, will be your host today.
Welcome back to the ODSC AI Podcast. My guest today is Dr. Denis Garagić, CTO at Palladyne AI, where he's helping lead both robotics hardware and intelligent AI software. Denis has a deep background in AI, autonomy, and event systems. Today, we want to do a deep dive into two major frontiers, embodied AI and autonomous drone swarms. On the ground, we discuss how adaptive AI systems are changing the way factories operate, moving beyond rigid automation. And in the air, we explore how swarms of UAVs are coordinating in real time like a hive, with planning and decision-making at the edge. Denis also shares why large language models often fall short in industrial environments and why hybrid approaches really shine. So with that, let's get into it. Denis, welcome to the podcast.
Thank you for having me.
And Denis, I'm very excited for this topic because embodied AI does enable machines, especially robots, to understand, reason, and act in real-world environments. But before we get into that, Denis, I want to talk a little bit about your career because you pretty much had a fascinating career trajectory. We were just talking about Kendall Square, and you were here at DARPA research programs at BAE Systems at the FAST Labs.
Yeah.
And you're also leading the pivot of Sarcos from a robotics company to Palladyne AI, an AI software company. So what was the kind of the pivotal moment? What made you realize that put you on this path?
One moment was a war in Bosnia, 1992. I had to escape. You realize that you're not really good in many hands-on jobs like construction, repair, cleaning. I was pretty good in math from my high school and college in Bosnia. So you realize like I better go back to school and try to use something that I know how to use, my brain. That was a pivotal. I entered the Czech Technical University in Prague in 92, not doing language, learning from scratch and learning very fast. But what fascinated me is really the field of, at that time it was called the automatic controls. Controls is really optimization, applied mathematics, prevalent in every aspect of society, for controlling motors, cars, markets, economy, and so on. Learning and understanding how to use mathematics to capture the sort of principle of feedback. We observe some, we process that information, and then we act. Whether that action is bad or good, that's separate, but then we keep collecting that feedback information and keep going more and more. So I kind of dive into that field, which obviously covered robotics as a general field. And at that time we called AI employee optimization algorithms. And so that kind of led me to this sort of principle of closed loop feedback that is really applicable across many disciplines. Then another pivotal moment, you graduate, your doctorate, and you focus on robotics. And that happens in a time of dot-com boom. And as soon as I graduate, nobody is interested anymore in robotics.
Right.
Everything is like, no, let's go back to something else.
Yeah.
Unfortunately, the power in computing wasn't there. The theory, the knowledge was there, but we were not able to execute some of these autonomous operations on that era computers. And then simply markets were skeptical about robotics autonomy at that time. So I pivoted to more still applying the principle of applying math optimization, but pivoted more toward really understanding how we make decisions when we need to account an opponent, how we actually adapt our understanding to the intention of whoever we face as either opponent or collaborator. That brought me back to the game theory, which kind of underlines many of the work that we do here in Palladyne AI in my previous work. And it's really understanding how you optimize your actions based on the intent either of your opponent or friend. That led me into the space of more DoD applications in which command and control is critical, but also applies across machines to strategic decision making. That evolution from every sort of DARPA program that kind of was published since 2002 till 2020 led me to many applications of really advanced technology and applying the same principle controls to molecules, decision-making, machines, sensors, and so on.
Yeah, that's an incredible journey. And I think a lot of our listeners can relate to the educational side of that journey. I graduated around the same time in electrical engineering. I dabbled a little bit in robotics and saw that even though I was fascinated with robotics, it was a pretty difficult field to break into. And boy, how times have changed. The hardware cost has absolutely plunged. Now I'm back into robotics a little bit. So things come full circle. Yeah. So if you don't mind, Denis, in this podcast, we've covered physical AI before, we've covered robotics, but not embodied AI. So let's start with the basics for our audience. Most people are familiar with generative AI models. How would you explain embodied AI and physical AI to someone who's just learning these concepts? What's the fundamental difference maybe between embodied AI and physical AI?
To me, physical AI is really the AI that deals with the physical systems. We are very familiar with digital world, ChatGPT, LLMs, even an image search these are all digital world environments in which we don't necessarily have to interact with any physical system. Anytime you say physical AI, now you have a physical system that you need to interact with. And that physical system is interacting indirectly and directly with the environment in which you operate. So that's set up for the embedded AI. Now you're putting embedded AI in that physical system, which means that you have to find a way to learn by interacting with the physical system and adapting as you perceive information from the physical system. So embedded AI is kind of also generic across physical system, but it involves really learning through actions. So you perceive something, you adapt your actions based on perception to execute certain tasks. Depending on the physical system, you may have slight differences. Embedded AI on drones is different than embedded AI on humanoids or pseudo robotic arms. But in essence, they still have to observe, they still have to come up with some mechanism to learn actions and apply those actions, as well as reason as the environment changes. And physical AI environment will constantly change. And that's really another difference with digital world. When you're in an industrial floor and the robot is operating, parts are all over the place. Those parts will change as you move them. You have to anticipate for those changes. Sometimes the sensors will be noisy, obscured. You have to be able to kind of see through kind of fog or sensing and still come up with action. On the drones, it's the same. Cameras can see through a cloud. Can you actually have another sensing modality to allow you to learn about that environment in which you need to navigate and perform actions?
So Denis, that's great because you're essentially telling us that embodied AI learns through its actions, as you said. It's got to actively interact with the physical environment, just like we as humans do, like animals do, and learn from those experiences. And of course, as you mentioned, they're going to need systems that use a combination of sensors for perception. Drones have cameras, robots need a sense of touch, something that we're looking at a lot at Cortical Ventures, especially my colleagues, Mike and Igor. And then, of course, actuators for movement. So creating that loop where every action provides feedback that informs the next decision. So really, if I paraphrase this correctly, you're describing embodied AI as transitioning from the digital realm to the physical world. Is it possible for you to walk us through another concrete example of this?
We currently have two software products that we are trying to allocate for the embedded AI for manipulation in robotic systems. So you need to manipulate an objects that are used in industrial environment. They cannot take place inserting or assembling parts. So those are all kind of sequence and sequential operations, but they're going to also change. If you drop the part, you need to reacquire. So if I kind of walk you on that side of kind of robotic manipulation requires interacting with the environment, touch, feel, force, moment sensing, and so on. And then there's a second application which more focusing on that drone aspect, which provides public safety or what we call intelligence, surveillance, reconnaissance actions, which doesn't require interacting with objects, but interacting at distance, which still requires you to decide how you're going to continuously detect and track and classify those objects or interest for the purpose of safety or some other actions. So let me give you maybe an example of the industrial environment. And we are very familiar with what we call cage robots. They were existing since 1980s. They're pre-programmed to do one operation over and over. And that's why you have them on the floor, about 3,000 robots. Each robot is allocated to a very specific action. And when you do this, you basically define your starting point, your end point, and then you just repeat that action over and over. So there's a really small amount of change that happens in it. Almost no change happens. That's why traditional robotics is effective for executing a single task. As soon as you change something, you have to reprogram. So you're trying to address that gap between something that's more deterministic and something that dynamically change that you need to be able to act without reprogramming and taking the robot offline. So there are many industrial applications in which, for example, sales order comes in and they are characterized by the parts. The parts are usually brought to the robot in a random configuration in different types of bins. And your task is really, for human, is really easy because they're going to recognize the parts immediately. The human hand is an amazing device. You're going to adjust your hand or arm adequately to take that part and place in adequate, container when that part needs to go. For robot to do this, you need to really enable them to be able to interact with the environment, learn, perceive, and then also reason and how to actually decide where to place those parts. So as you kind of bring these parts, so if you random configuration, find the best orientation of the part, best grasping location, depending on your end effector. Given that, you need to find the best path that will avoid obstacles, that will avoid dynamic obstacles in the scene, which you may run into, and then find the best way to place the part in a corresponding sequence that will then be taken on a production line into assembly. So you can see that there's a lot of variability in that space. Variability is almost enemy of traditional robotics because they don't account for those. Now, with the approach that we are taking, we are using multimodal sensors. When I say sensor, perception is not only computer vision, but it's also kind of sense of touch. Force moment is critical for robotics because your end effector will be able to sense force, like avoid damaging parts, but that also becomes critical for adequately grasping or handling objects on manipulation. So all of those things are happening kind of in dynamic way, in a way that needs to be optimized over and over and not kind of pre-program all determinists. So our approach is to be able to accommodate variability, accommodate those sort of uncertainty, comes either from sensors or comes either from the obscuration in the scene, and still find a dynamic way to accomplish this task within the certain cycle time. In industrial application, determinism is desired because you can now assess repeatability of your operation. Then determinism is really also detrimental for the varying dynamically changing scene. So you have to find a balance. Do you actually do this sort of allow variability to excel, which kind of gives you the adaptation while still satisfying some form of determinism industrial application like to have. In many applications, you need to have a repeatability accuracy of 99.9%. We can address this later on with foundational models. None of these approaches are even close to that accuracy. So we are trying to balance the requirements from the industry and sort of accommodate that while still maintaining that sort of variability that needs to be captured. On the drone side, the key part there really is again perception, perceiving environments with multimodal. When I say multimodal, means cameras, means electro-optical infrared, means radars, or the passive, receivers, all those information is the same as we perceive environment. Even if you close your eyes, and if you hear somebody, you will be able to build that picture of somebody because you will be able to retrieve those features. If Joe closes his eye and doesn't have other modality, most likely will crash unless you force it into predetermined path. So it really starts with a kind of a sensor package that allows you to perceive our environment under different conditions. And from those, you are able to kind of provide that representation. Representation is also a critical part. Again, humans have amazing ability to characterize objects, scenery with a very limited number of features. We store that in a very limited memory and have amazing ability to retrieve and associate those, then right sensing capability comes in there. So that's a similar kind of principle with the drones. We're trying to our goal is to detect, track, classify things on the ground. As a result of that, you want to be actively controlling drones to maintain that situational awareness. And that kind of happens on an individual level. But then if you collaborate with your teammates, then you also have an ability to provide that continuity. If I lose one modality in sensing or temporarily lose the picture of the, let's say, car going through a tunnel, I may want to use that collaboration to help me. You can see there's a constant interaction between sensing, environment, and adaptation to those actions that you can actually provide the best optimal way of executing tasks. Obviously, there's a component of learning, there's a component of kind of inferencing. We are trying to get to the point in which you can actually learn in situ, especially on the drones. We don't have the ability to kind of emulate, simulate all possible situations, environments in which you can be thrown. So with limited data, you want to learn how to behave in that environment. And that's another key component of our approach to embedded AI, is really that sort of training or learning to perform tasks with limited information.
There's a ton to unpack there. So let me just touch on a few of those points. Your last point there around drones, we can see in the news, that's a big topic and we'll dive into that later. Going back to your early comments, that term caged robots, I'm unfamiliar with. But I do like that term because I've gone to at least 3 or 4 robotics conferences in the last couple of years. And I've been kind of disappointed because most of these robotic conferences just have robot arms affixed to someplace, which makes a lot of sense. They have to do a certain job in a certain area. And I have been following what Google's been doing with their Gemini robotics models, and that sequential reasoning you talked about was so important because it showed a video of a robot arm, which I'm trying to actually build myself, sorting different objects of different colors into the correct color basket, folding a shirt on a table. So again, despite what people say, the robots are getting better. And then forget about physical AI or embodied AI for a moment. Even in the digital AI realm, we're having arguments over like, we need our AI models to be creative, but we also need them to be deterministic, to have competing goals. And a lot of times people struggle with that. But instead of talking about non-deterministic, I like the way you phrased it. You're talking about embodied AI systems having a degree of determinism, right? And of course, in factory settings, that degree of determinism is very important for certain use cases. So I think I agree with you. Embodied AI is not great for certain use cases where there's a high degree of determinism. That's why you need more planned robots. Is there a hybrid alternative?
Yeah. Balance this between, I like to call it almost hybrid approach, because you can see in physical intelligence, if you watch some of those videos, they're kind of going into that direction. They're putting more and more symbolic reasoning to improve reliability and also reduce the amount of data that you require to train those models. We can cover that topic. I am very concerned that, in digital world, we have, as individuals, willingly given our data to internet. Your email, your Facebooks, everything is out there and it's all digitized. We have given that stuff into the sort of worldwide app. And I think that logic have driven these very gigantic deep learning models to harvest the data. And if you have the data in the pristine form, you are able to create amazing models that will create variations or combinations of things. People are fascinated with those. But at the end of the day, are they creative? Are they critical in thinking? They're getting better because we keep feeding them more and more data. So that's kind of digital world. I think that kind of model may be relevant there. But imagine going back to the physical world. First of all, you're facing with proprietary information industrial environment. I don't think the customers we currently deal with would like you to give to the internet a design on the engine. or parts they need to make. I don't think they will be willing to give you a description of the environment in which that robot lives or set up industrial environment. They don't want even to connect you to cloud or even private network on their NAS. You're basically forced to live at that edge computer with very limited data. And by definition, defeats the purpose of foundational models because you cannot train them on anything. That's one side. And I don't think that's going to be, maybe in some near future, we'll be going to give all our robotics data, all of our interaction data in a physical environment to that space. But then at the end of the day, you still have an issue with compute power. My company is not NVIDIA, it's not Google, it's not Amazon. I think Meta recent Llama model was trained on 600,000 GPUs. That's basically 60,000 for each of those. I was in a conference a little bit 2 years ago, and a representative for this company came and they said like Llama 1 was trained with 6,000 GPU. We are going to 600,000. So to me, this is like exponential explosion in computing, electrical engineering. Computer science is all about how do we do polynomial logarithmic increase in computing resources and everything else. So something that we can manage, right? Anytime you measure an exponential explosion, everybody freaks out because that means more and more money, more and more computing. For the small companies, dealing with that diversity of tasks that you would face in industrial environment and requirements on reliability, as of now, really puts a lot of pressure on foundational model to gain this. You will have to collect large quantities of data. You will have to somehow pass the cost to somebody.
Sorry to interrupt you, Denis, but that's why synthetic data is emerging as we know it's not a perfect solution.
Synthetic data is the point, but that proprietary information your customer is giving you about their scenario.
Yeah.
Emulate, but most likely they want to keep that for themselves. They don't want to be sharing that information training. Synthetic data is definitely good. You still have to compute resources.
Yeah, no free lunch.
And that's for small companies investing, that's a huge amount. And by that point, like, if I'm charging yearly license for my existing software that has a kind of components of hybrid approach, and then if I'm asking customer to pay for additional training of those foundational models with 85% accuracy, that's a hard sell for me. And that next topic is really that reliability of the models. If you kind of look at literature, reporting is really poor. I mean, you're talking about accuracy of maybe 92% for some tasks that require 99% accuracy. And I think we can get there. People will say, I'll throw more data in there. Okay, that's one method. Or come up with something that's more kind of hybrid. So really our approach is to say like, can we use combination of also optimization-based AI and then throw in foundation models to really cover some of those edge cases. So it's almost a complement to the approach that we know will perform with certain accuracy. The training is becoming better, transfer learning is becoming better, all of those things, but that requires still sharing those models across groups. Inference is still a big issue. 50 billion parameters model cannot really run effectively at 500 hertz that I need to send to my motors on a rabbit. Those are all considerations. I think it's very appealing to see videos sped up 4 times folding the shirt.
Right.
But then when customer asks me, can you fold the shirt 100 times the same? And not like second time, you got to fold it, but it's got to be slightly different. My customer, when they receive the package, they're going to say, well, I don't like this stuff, right? So I don't want to buy it anymore. I'm not denying technology is great advance, but I think we also need to think about, do we have the right AI algorithms that can function on a limited computing and capture that sort of the mystery of the scene that's required for adaptation. And I'm not fully sold on deep learning techniques that do this brute force with just data, feed more data, and everything will be fine. It has to be some form of adjustment, some form of additional inputs to help you navigate. And maybe we don't need to be as generic as possible. We can be generic within a few tasks and do those well. And maybe that's a better way for, I'm talking mostly about industrial applications. I'm not talking about housework or assistance.
Yeah, it's a fascinating conversation. Talking to people at Google, talking to people at Physical Intelligence, everything you talk about, the cost of inference, the difficulty of doing AI in the edge, which Embodied AI is a great example. But I do wonder when they're building on these cross robot models or cross functional models that control multiple robot types, like it's very difficult to cross train a robotics model of these generalist policies that can have different robots do different things because there's a school of thought that's a dead end. I'm not so sure about that, but I'm wondering if there'll be a moment in robotics where someone releases some cross robot models and all of a sudden we don't have to do inference and we can avail of transfer learning and fine tuning methodology.
If you go to serial robotics arms, they are fairly standard physical parts, right? 6 degrees of freedom, 7 degrees of freedoms. We know how to control them using traditional Newton dynamics. You can do many optimization-based things are very adaptive, and I would still call them AI-based, but they're not necessarily foundational. So what I'm afraid that we are forgetting about that whole knowledge of physics, because we build those devices, we know them. Why do we have to reinvent the wheel, teach them and learn from them from scratch? My philosophy is that work actually in our lab on exoskeleton, which I believe is probably most complex humanoid ever built in the world, 36 degrees of freedom. And it's not built as a humanoid, it's built as an exoskeleton that needs to hold a human. Kinematically, it's awkward to be a humanoid, but we have actually created that humanoid that can actually be hybrid. You can be in exoskeleton, you can step out with your both.
Sorry to interrupt, Denis. It's actually an exoskeleton that a human could wear.
Yes, it's an active exoskeleton. This is what Sarko actually was on for a long time.
Yeah.
We went through prioritization and then COVID hits us with all the supply chain issues. But we were always developing the software that we want to actually harness power of that human. It's amazing how human, when you spin a machine that's like about 300 pounds heavy, you don't feel that's obviously weight, but it's amazing how human is intuitively adjusting hips, intuitively adjusting knees in order to maintain the stability. So if I were to say I'm going to do brute force and try to apply all possible training methodologies, trial and error, fail, go again, and so on, why not just harnessing that kind of essential human understanding of motion? So now you have a kind of prior knowledge to start with and much less need for data to build on top of it. My point was, can we use something less exploratory, but more success-driven based on our understanding and sense of motion and action execution? Our embedded AI is capturing what we call success-based learning. I'm only capturing what's successful with a small amount of failures, but that gives me the ability to really quickly learn at least motion in complex situations, but also you can also learn complex execution along horizon tasks. What's called in robotics as a kind of holy grail of how do we execute a long horizon task using foundational models, for example. And that requires a lot of sequencing, a lot of teaching. Going back to robotics and generalizing, robotics are physical devices. What is different between those physical devices is really that end effector. How do you actually now account for all possible combination and effects? If that was a human hand, which we still don't have a good end effector resembling that, we can generalize because every robot will have it, except that type of hand will cost you probably $150,000. And, if you pay for a robot $50,000, do you really want to put a hand of $150,000 that can only lift maybe 5 pounds? Probably not. So now we have a diversity of robotic systems, kinematics, and the factor that you need to interact with the space, and also diversity of the sensors. So now you need to collect all that information. The question becomes, is it relevant to teach robots 6 degrees of freedom arm? Probably not. But if people want to generalize, they're going to keep throwing more and more data in there. I don't know how we started there, but my point is we have experience with, and for my colleagues in different companies, they often end up going to really one robotic system. And especially if they're making that robotic system that's humanoid, why would they have to capture humanoids from all other companies that they can't even describe those ones? So maybe focusing on one particular robotic system and kind of trying to make that system generic, maybe it's a better approach than trying to create a model for everything. In that case, your model is smaller. You'll be able to perform that inference on the edge computer. You have some chance. I still believe the hybrid approach is right because I don't think foundation models will solve everything. It's kind of hard to believe. I believe in science, technology will get better. But right now, from pixels to motion, I think there's better ways of getting there. instead of just feeding pixels and creating actions. You have to have some intermediate steps to help.
No, I 100% agree with that, because we're seeing that in the digital AI world as well. Whereas we're ditching rules-based programmatic systems for non-deterministic systems, and then applying rules-based systems to the outputs of those non-deterministic systems to make them acceptable. And then what would you say are the three most important capabilities that distinguish embodied AI systems from traditional programmatic robotics?
I think the key is that the underlying principles are completely right. You are going to observe something. You're going to learn from interacting with that environment in which you operate. And based on that interaction, you will come up with optimal actions. But the question becomes, how much data do you need to get to those points? And I think that's a critical question that we need to, as a community, really think about. A really good example is drones. I mean, you cannot control the environment in which you're going to push the drones. Look at the war in Ukraine. I don't think they can emulate every possible scenarios which they're going to face in the war.
Yeah.
That's my point. When you perceive what is the mechanism that we need to have in embedded AI that learns, adapts quickly with limited data. My main point is like, we need to still really examine, do we have the right approaches to the embedded AI techniques? You know, we've been using deep learning, we've been using reinforcement learning, we've been using all those things, but most of these models are very data hungry, I would say, computation hungry.
Yeah.
So can you say within the same principle, but really work on a sort of models that generates adequate results, but don't require that humongous amount of training and computing. And I think at least Palladyne AI, we made some strides on that front. We have publications on the drone side, but that also applies to robotics as well, really applying what we call online reinforcement learning. Learn as you go through the scene. Being in a kind of autonomous flying that is working because time scales are a little bit slower, that you need to move the manipulation options within milliseconds. So I think that's the key components of embedded AI. It's a great idea, great principles. We just have to still figure out how do we actually get right techniques in that mix.
You're going into areas here that I really find fascinating, because I've been actually reading some of your blogs, some of your work and your company's posts. And I was fascinated by what you mentioned, the online reinforcement learning. For our audience, online is kind of like in production, offline is out of production. So online reinforcement learning for drones is pretty fascinating. And that's a technique where that drone learns and adapts its flight behaviors in real time during actual operations, instead of only through pre-training or simulation or pre-recorded data. And those drones, from what I read in your post, they're continuously tying actions and observable results from their sensors and adjust control policies, right? So we're still dealing with autonomous machines, so they still have policies to maximize those rewards. But also, Denis, in a recent blog post, which I'll link in the show notes, you made this quite fascinating distinction between true biological swarms and what everyone's calling drone swarms. I think you said they're merely puppets. Can you explain what makes a genuine autonomous swarm fundamentally different?
Yes, I wrote that blog, and I think that biomimicry inspired optimization, also called evolutionary optimization, for a while. Swarm comes from that biological analogy. It's really key characteristic of swarming is decentralized decision making, which includes selfish individual agents. Each ant wants to eat, each bee wants to collect pollen, and individually they want to do this best they can, but they also figure out if they do collectively, they will achieve that goal much faster. And as a result of that, they start to provide sufficient information to their mates, but not overwhelming them, so they don't know what's happening. So if you want to have a teaming of many drones together, they have to be able to self-orchestrate, because having 10, 100 drones and trying to predetermine what they need to do is not scalable. Our principle is really, we have to capture biological swarms, biological entity, and communicate with limited information. They don't exchange data. Data is usually associated with huge amounts of time required to transmit bandwidth over the comm signal, but they really dissect what they want to inform their teams. And that information is usually in kilobytes. So our principle is the same. But what drives that communication is really that need of individual to communicate with somebody. If you are in the group and we are watching, let's say, I don't know, soccer match. Many of those people watching, they want to be satisfied watching the soccer match on their own. As collectively, they're going to get excited and that brings their attention and they get happy. Disappointed, like collectively, getting disappointed collectively is much easier for individual. Our principle of swarming is trying to kind of stay within that biomimicry biological component because it requires least computation, because it requires least communication, which means less bandwidth. All of that enables us to stay in air longer because more you communicate, more you compute. You use your batteries or your whatever engine fuel, and you have to either go back or you're going to drop all the stuff. So the same applies with the bees. They're going to collect pollen, but they're going to collect enough pollen so they can go back and drop it and go back again. Our principle is really, I'm going to focus that each individual is independent and sufficient to do kind of autonomy on their own. Only when they need to, only if they're going to gain something from collaboration, they're going to start to collaborate. And one concrete example is if you dispatch drones to observe something on the ground, individual drone will only be able to observe within that field of view of sensors. But if they start to lose at objects, let's say object starts to go through the either overpass or turns in some other directions, then perhaps they should be able to communicate or collaborate. Somebody capable of observing the target so they can have a handoff of the objects. So if you follow that principle and then add this component of game, which means that I'm assessing capabilities of my collaborator, I'm not going to collaborate with everybody. I'm going to try to collaborate with somebody that makes more sense to me. And, one intuitive example is just the closest that you have next to you, because that will mean least energy exerted. So those principles are driving that collaboration, self-organized. Now, if you're facing your opponent, you're also going to be estimating the intent that will also drive your actions. If you look at what people call swarming, and then you see pre-organized patterns, even in parse games, all those things are pre-programmed previously. Maybe they were just small modifications, but they were not self-organizing in a way that will create something meaningful. Centralized coordination, no central point, because every time if you have a central point, you need to feed that information back to the ground, which means you lose power or you're going to deplete your power faster. I think there's obviously goal of the central point because they can define the goal. And that's goal for ants is to find the food or to build an nest. Goal for bees is to find best pollen and come back to the hive. So the same applies in the swarm principle. You define a goal for individual objects, which in case of intelligence, surveillance, or reconnaissance is really provide maximum coverage of objects on the ground or focus on a particular things of interest. As a result, you have self-organizations with limited communication because they're all self-driven, or I call them selfish agents. They want to maximize their returns.
Nice. I like that term. I'm really grasping this concept of goal-oriented online reinforcement learning you're talking about. And going back to what you said, this optimization of an individual's machine to communicate. I haven't thought about that too much, but you're absolutely right. The more to communicate, the more bandwidth they're consuming, the more compute they need, the more time it's taken. And that may be deviating from the goals. It's a great example of that concept of self-organization, but also decentralized intelligence. Because a lot of us think about AI, like we talk about AI, it's so different from the way I think about multi-agent systems, right? In multi-agent systems, we're thinking about a planner, a worker, and MCP servers, and they're all communicating to each other. And that is actually a problem now. Communication bandwidth and passing memory around and where that memory is adding to complexity and the huge stack. And now you're painting a very clear picture of something similar. So maybe when I do my next multi-agent architecture, I'm going to think more about what you're thinking about, the importance of a decentralized brain, so to speak, because this is a really hot topic of research. Let's say you've got a drone swarm involved in search and rescue. When people are searching across vast areas of ocean and mountains, like that's a good example. So you talked a little about that, but what's the optimal way for a swarm to negotiate with each other to decide who tracks which target or in which direction to go? How would that work in practice?
Yeah, so it depends on your individual goals, but also how you define that objective. You don't want to also limit yourself to sort of one type of, let's say, vehicles a team, because small drones, they're going to last only a limited amount of time. The larger drones are more expensive, but they're going to be also more persistent. You also have to think about this heterogeneous configuration of your teams. and how they interact, because they can also feed each other. Our theoretical background for all this is really game theory based of that basically is embedded in AI. So if you think about reinforcement learning, that reinforcement learning reward accounts explicitly for your opponents, but also through your collaborators. And as a result of that, imagine I'm going to be tracking things in one region of interest. I'm going to allocate certain number of drones to do it. And their goal as a group is to provide persistent coverage. So not redundant coverage. I don't want 5 drones in one object, unless I'm telling them that's a really important object. I want them to be covering without redundancy. So that forces drones to be in that sort of configuration, self-organization. I have a target. I know that my neighbors potentially have a target to be covering all this. As a result, you have a full coverage. Now, if the targets are moving from one area to another area, and you have another group of vehicles somewhere else, you will hand some of that information back to the other ones, which will then again, their goal is to do this persistent sort of coverage, or what's called in the public domain, security handoff of objects. Sometimes police is watching a car and a person steps out. If they have a drone, they can only focus on one of those things. Then we have demonstrated this to the public safety. Now suddenly you can hand off those targets between multiple drones and provide that persistent coverage while still using a single operator as the monitor for that situation. There are definitely mechanisms in optimization that we use. And again, the key there is really account for that intent of your collaborator, but also of your opponent in order to optimize your actions. And I can go into any level of details on that topic, but the reason I mentioned the game theory, and it's an amazing mechanism to optimize your AI models, because they become in tune to the fact that you may be facing intelligent opponent, you may be facing intelligent collaborator, and the results, you need to also adapt your actions based on those results.
That's so fascinating, this concept of game theory that can be used in controlling drone swarms. And obviously you can use that to optimize coordination resilience. Yeah, I would love if you could talk a little bit about game theory for drone swarms in both defense or adversarial scenarios.
In a game theory, you usually have opponents or a collaborator. And different theoretical concepts of non-cooperative, cooperative games, we combine them together. But the key there is really estimation of your opponent's intent, because you don't know that objective function. The economic games, we say players are rational and they want to maximize their profits and minimize their losses. So, at that kind of high level, that's your objective of your opponent and myself. But many times you assume that you know objective function of your opponent, so you can come up with a strategy. But in adversarial environments, you will never know intent of your opponent. You need to infer or learn that behavior from available information. So even if you are technically tracking your objects, and if you have a multimodal sensor, sometimes these objects project different characteristics that may, over time and space, you realize they're doing something suspicious. So now you can actually discriminate what is suspicious, what is not suspicious, but also at the end, you estimate the intent, whatever that intent is, good or bad. If you can estimate that intent from sensing capabilities that you have, then you are able to come up with a strategy that perhaps will outlast that opponent.
Yeah, I'd love to hear an example.
Example is electronic warfare, for example. I mean, you can estimate the intent of your electronic opponents. If they're going to try to deny you a signal, you can avoid a signal by adapting your transmissions. The same applies for the drones as well. If you can estimate the intent of the opponent, you'll be able to proactively go into the area where you may expect them to show up next, even though they're lost for a couple of minutes or even hours. So when you kind of make decision on your own, anytime you didn't account for the factors that, let's say you want to call repairman and you assume that repairman will show up no matter what because you got to pay them. If you start to do a little more research and you figure out, well, this repairman had received bad rating, then you start to account for the fact that you may not call him because now you're changing your actions. And so every time we account for that sort of possibility of facing opponents or collaborator, you are able to adjust your actions based on those. I don't want to go into the details of some of the applications that we deal with, government's work.
Understandable, yeah.
Or public safety. Sometimes you're chasing a car, sometimes you're following suspects that are not suspects, and you don't want to be intruding their privacy either. So if you're able to estimate that intent, and that goes back to kind of ethical component that we're trying to do, is really that we're hoping you're going to be right in intent, but if you don't, you're going blindly after somebody that you may consider suspect because they drive like 60 miles in an area of 35 miles. So that's the measure we use to optimize our performance, but also follow this ethical component, especially the surveillance applications, and be able to adjust our actions as a result of those.
One of the areas that we're definitely fascinated with right now is anti-drone technology, because you can obviously see what's going on, as you mentioned, Ukraine and what's going on in Europe and all the airports there being shut down because of drone sighting issues. But coming back to the adversarial games, speaking of football or soccer again, World Cup, but I think but $500 million have been allocated to anti-drone technology for safeguarding the stadiums at the World Cup. The game theory you're talking about is such a powerful tool if it works. I'm not saying it's not, because you're kind of convinced me, but it's such a powerful tool for anti-drone detection systems. Part of my role, I talk to some startups, and one of the things that I hear about is pursuit evasion models, like adversarial drones trying to survey something, and then all of a sudden it scoots away. How do you figure that out? Something I read in one of your blogs also brings to mind, because you described this scenario of a drone swarm. So what happens if a group of drones in a public safety scenario detect a number of different adversarial drones and they go in different directions? Like you see in Ukraine, the high use of dummy drones and decoy drones. So obviously the adversary be trying to do different things. There could be a number of decoy drones flying around, and then that split decisions. I think that's an example of how complex this is getting very quickly. When people start talking about anti-drone technology, once you start to peel back the layers, it's an amazingly complex subject and topic.
Yeah, I mean, anti-drone technology, previously we had a few programs in US Air Force, which deal with the counter measures, but there was more kind of physical when you actually send something to go physically against those. And I think that concept of what we're trying to do now is really, do you have a technique that will actually estimate, again, the intent? And if you know that, you can actually place first proper number of perhaps counter drones to go against those, or proper number of ground assets that will be required to defeat those incoming drones. In public safety, it's a little bit sensitive topic, but the best thing is like really somebody's in a car, drives, drops somebody, comes back a couple times, picks them up. And again, if you don't have that persistent capability to see all those actions, you're going to lose that sort of component of dropping them off, right? Coming back and picking them up. And this is where we demonstrated to a few public safety departments, like if you even have 2 or 3 drones, you will be able to provide the persistency, because they will kind of try to reallocate themselves without commands.
Sorry to interrupt again, Denis, but that still puts a big burden on the drone operator where it's a single operator.
So if you use what's currently used traditionally, because it's basically one operator and one drone, they only can focus on one thing. And basically if the object is out of the field of view, they will have to go to the second drone. What we are doing, we are enabling a single operator to observe what's happening as this sort of kind of swarming is providing situational awareness. So in that case, the drones will self-organize, split to follow those 2 different objects, but the user will get a collective picture of that. And that user will be able to get understanding what's happening. In public safety, action is really driven by that operator on the loop, because it's a privacy. They're not going to send drones to go after that car. They will have to decide whether to dispatch police car or to actually inspect those. So there's always this feedback loop, especially that includes an operator on the loop. In that case, you are providing sufficient information to a user so that user can create that action. And action usually involves public safety officers.
Yeah. No, I got to say, I do admire the work you've been doing. I've been following drone technology for the last 3 years. I'm obviously also following the debates in AI around AGI. I'm not sure if you read that recent book. I haven't yet, but very interesting title. If they build it, we all die.
No,
Basically, the title is saying if they build AGI, we all die. But I've been on record that I think AGI is a bit of a distraction versus general purpose intelligence. I think people are not paying enough attention to what's going on with embodied AI, especially around drones. And that really is scaring the bejesus out of me. What I'm always thinking about is what's going on in industry and government right now, like the ethical considerations, the safeguards. And of course, just look at what's going on in Ukraine. The horse is already bolted, but anyway, it's never too late. But is there any conversations about the need to put safeguards and ethical laws around deploying these?
yes, definitely. Public safety, even in, again, different militaries have different rules of engagements. I can speak with some level of understanding for the US, but there's obviously that kind of importance of the human on the loop. And again, we are enabling human to expand capability of individual when they actually observe this. Again, like if you look at even current rules for operating drones, it's one-on-one, and that's not scalable. So being able to say one-on-many, so that operator is still on the loop, still be able to kind of create a final decision, whether that's military or public safety, based on information that these drones autonomously provide to the user. And there is a sort of a professionally trained officer that is assessing that information provided by the drones. But what's makes his life easier is that drones operate autonomously. So he or she doesn't need to control in order to obtain that information. Now information flow is coming back to them, and their decision process, I think it's less overwhelming, but more informed. And they follow their rules of engagement and follow the rules of law as a result of information. If they had to manually operate and gain that information, then do this for multiple, they will get overwhelmed with the quantity of information and probably make poor decisions. That's one aspect of ethical guidance. Certification is not only performed based on one single set of modalities, performed on multiple of those modalities, but we are also introducing kind of additional guidance in there. Instead of instantaneous detection, we want to observe that over time and space, because then you can kind of build the full picture of behavior of either suspicious or, let's say, civilian military target, and so on. The safety, obviously, on the robotics side, there's always safety. Safety is first. We try to gain in reputability and accuracy, but the safety of application is key. Following safety in terms of reach space, in terms of speed, in terms of reachability, these are all kind of already embedded. The same applies in the drones, geofence, obstacle avoidance of collision between teammates. These are all critical for public safety domain, maybe less critical for the adversarial environment. But those are kind of embedded in there. And then notion of bias and privacy and proprietary information is really the key for our ethical stuff. Like I was mentioning earlier in robotic manipulation, embedded AI, we are very conscious about customers' private data. That data is proprietary to them. That's why we're enabling them to train the models at the edge. We are not mixing data from different people, different companies. We are intentionally telling the customer, you're in control of your data. If you want us to help you with those, that's fine. But you're owner of that data and you have all ability to train the models and own those models. So in a sense, like those are kind of main characteristics of, well, I would say like, ethics and safeguards, at least our approach to embedded AI.
I think that's very well said. And I think it's accurate to say that the adversaries using drones always seem to be ahead of the defense or anti-drone countermeasures, and a lot of factors there. But I do want to lift it back up, because we could go down that rabbit hole for a long time, but I do want to lift it back up to embodied AI, because I did talk earlier a bit about world models and if they help or not. But John LeCoux and others talk a lot about world models.
I think I mentioned earlier, I don't believe that foundational world models will solve what I need to solve for industrial customers. And so that's why we are taking this kind of hybrid approach, in which we have a sort of approach in which we still observe, learn, and adapt using different AI techniques, and then use these embedded or world models to supplement us for the really edge cases. And those edge cases are kind of rare, right? They happen occasionally, but that's also important, because then data is really pristine.
Yeah, you're right. For a cage robot, as you so eloquently put it, but what about robots where they're trying to operate in a home environment where it's the exactly the opposite. It's an uncaged robot.
Even applies also for the non-cage robots. I don't think we can anticipate all the actions. What we need to guarantee is that robots, let's say human, have to guarantee stability of live motion. Foundational models, we know how to solve that either through reinforcement learning or through optimization-based techniques. What you need to account is really changing of the scene as you perceive. And so what I'm suggesting here, there's a way to capture that quicker with less training data by using actually human as a demonstrator or providing that instruction. That's how we base our models. We use demonstrations. Demonstrations are captured into kind of probabilistic model that's much constant to the difference, but still accounts for variability. Then we have those edge cases. Let's say you drop something or you accounted on a different setting that you didn't see before. Maybe those foundational models can help us generalize and create a sequence. Now, again, this kind of philosophically a little bit different than feeding data, creating models. You like to say, as a human, we have a set of tools. You know how to walk, you know how to write, but you learn those using these little, what I call them primitives. Each time you use that primitive, you use it differently to create new primitive that's more complex. So our principle is really, can we have a limited amount of primitives that we can either teach robots through demonstrations or through experience, and then actually stitch them together as they perceive the scene to generate that sequence of operation. You still use machine learning models, they're much more compact in representation, but then you're using also power of association to perceive scene. Inferring your actions by combining the limited number of primitives. You can have a limited amount of things, but you can create many variations of that. So our goal is to create a team frame that will create almost infinite number of solutions from very limited and compact representation.
Interesting insight, Denis. I really like that because my final question was, what do you see is coming next? But I think you've already addressed it.
You know, there used to be a really good conference, similar if it still exists. There was a really good conference called the Neuro-Inspired Computing Elements, called NICE. And we would have these workshops, limited number of people. And I had a few DARPA programs with trying to kind of either create hardware that would enable that narrow-inspired computing, like neuromorphic hardware or Bayesian type of analog devices that we can put in machine learning algorithms. But we always focus on that sort of representation. What is really cognitive neural computing? Our brain only uses 20 watts of power. That's used for muscle, for thinking, creation, for everything. Take, I don't want to call the names of the company, but you can take like even simple jets on board, that's still 30 watts of power. And so my point of that conference, when we went, a few cognitive scientists really sort of not happy how, for example, deep learning hijacked their field. They felt like, you know, neural networks by definition doesn't mean that's how we compute. It's almost like we sidetrack ourselves by saying this is a solution for cognitive and human-like computing, but then we drag these big servers with us, huge amounts of training data. Humans are amazing in that computation principle. I don't think we cracked that mystery yet. How we store information, we don't store gigabytes and terabytes of data. We store representation, but then we use amazing mechanism of association to retrieve that information and construct new objects and new realities. I don't see techniques coming up. I was hoping that, you know, with some of the DARPA initiatives, that's going to become more prevalent. I think people are also going to more like a pragmatic or practical, hey, what the GPT is working, why can't we just keep going this way? But then your computing is going to explode exponentially. So by the end of the century, we're going to have a nuclear reactor feeding power to each of our data centers. It's going to be
by the end of the century, they're working on it right now.
I think it's not scalable, especially for physical AI, because you have to have a small compute device that you can carry with you. A humanoid cannot be on umbilical cord, even connected to cloud. Cloud is sometimes not prohibitively expensive. So my point is, I think we need to find a possibly alternative approach to different AI techniques that will capture this kind of true essence of, I would say, cognitive computing. We are working on neuromorphic computing, trying to map some of our reinforcement algorithms into neuromorphic chip, which is based on the principle of, I would say, brain computing, spiking neural networks and reacting to the events rather than just simply ingesting all data at once. So yeah, we'll get there. If you can crack memory, data representation, association, then we have a chance to create something that's lean and cooperative.
I like the name of that conference. A pretty cool conference. They were saying that neural networks hijacked their field. I definitely feel like neural networks has hijacked my life for the last 10 years, but I'm not complaining about it necessarily. Neuromorphic computing is super interesting. I haven't paid too much attention to that, but it's one idea that we're using hardware to mimic the computer brain is a pretty cool concept. Denis, this has been a fantastic conversation. I would apologize for running over, but I'm not going to apologize because again,
no, it was really good. I appreciate your time as well.
Yeah. How can people follow your work?
I publish occasionally when permitted. The conferences, the best way is to monitor our website. And it's not that huge in quantity, but we're trying to be conscious of not overwhelming people. But I think the best way is to kind of monitor our website, press release around more related technology. And then we usually announce either the programs we got funded from the government or some of the latest stuff we are releasing. Publications are out there. It's always
excellent.
Yeah.
Well, Denis, thank you so much. This has been an education in embodied AI.
Thank you.
This episode is sponsored by ODSC AI East, the premier AI Builders Conference coming up this April 20th to 30th, 2026 in Boston and virtually. Learn more at odsc.ai/east, and don't forget to use the code podcast for an exclusive 10% discount. Supporting our podcast by subscribing not only helps our small dedicated team at ODSC AI, also unlocks exclusive benefits for you. Your engagement directly contributes to the growth and success of our community. Please subscribe now and don't miss out on the next enlightening episode.